All right, everyone. Welcome to lesson 23 of this semester. Although I guess this is less of a new lesson and more of a review of what we've done so far. So we've learned many different series tests at this point. We've learned about the test for divergence, alternating series test, both of the types of comparison tests, geometric series tests. We learned how to deal with telescoping series, and then the root and ratio and integral and p-test. So there's a lot of tests that we can use to analyze if a series converges or diverges. So what we're going to do today is we're going to just practice using these tests. And probably one of the questions I get most often in this class is, how do I know which tests to use at any particular time? And honestly, the answer kind of comes from practice, although I will be discussing as we go along some identifiers in series to let you know which one to use when. So there definitely are some clues you can use to tell you when you should use each particular series test. All right, so what I'm going to do is I'm just going to go through a bunch of different series and I'm going to explain how they converge or diverge. All right, so let's start off with the sum from 1 to infinity of 2n plus 1 to the n divided by n to the 2n. All right, now for this one it's pretty easy to select what to do here because we see we have nth powers everywhere. And whenever we have nth powers everywhere, that says to me root test with all these nth powers. All right, so let's go ahead and use the root test here. So that's the limit as n goes to infinity of the absolute value of our sequence that we're adding up raised to the 1 over n power. Now everything in here is positive, so now we can get rid of the absolute values. And if I apply the 1 over n power to each of these nth powers, those will all cancel out. So what I end up getting is the limit as n goes to infinity of 2n plus 1. Now the 1 over n cancels with the n, but it doesn't get rid of the 2 in the power. So I have the limit as n goes to infinity of 2n plus 1 over n squared. And since this is a limit of a rational function where the degree of the top is less than the degree of the bottom, this is going to end up being 0. Now remember, the criterion for the root test is that if it's less than 1, we know this will converge. And if you care about this, it converges absolutely. So that's what's going to happen with our first series here, and the big giveaway was our nth power right here. All right, let's move on to another one here. Let's have the sum from 1 to infinity of negative 1 to the n, and then we have n over n plus 2. All right, now whenever I see an alternator here, that obviously tells me that the alternating series test might be a good idea. But if I look at this, what is this going to as n goes to infinity? Well, this is going to 1, right? Because we have a rational function with the same degree and same leading coefficients on the top and bottom here. So I'm just going to look at the limit of the whole thing. So if I look at the limit of all of this, well, this is going to 1, right? So this is the same as the limit as n goes to infinity of negative 1 to the n times 1, or just negative 1 to the n. But this does not exist. Now, if we get something that doesn't exist for the sequence, that means it's definitely not going to be equal to 0. So that means that automatically we can say that this series diverges by the test for divergence. So don't be led astray by the alternator here. If you suspect that the stuff next to the alternator won't even go to 0, then try test for divergence first and see what happens. All right, here comes another one here, another alternating series. N is 1 to infinity, negative 1 to the n over n squared plus 2. All right, now with this series here, we see it's alternating again, though this time we have a rational function with the degree being less on the top and greater on the bottom. So this will head to 0. So what I'm going to use is I'm going to use the AST here. So if you suspect your thing is heading to 0, it'd be a good idea to use your alternating series test. So we need to see if it's decreasing to 0. So is n over n squared plus 2 decreasing? Well, yes, eventually at least, because the bottom is growing faster than the top. And is n over n squared plus 2 going to 0? Well, let's see here. Like we said earlier, we have a polynomial with lower degree on the top, so this will go to 0. So this converges by the alternating series test. So if you only care about convergence and divergence, then alternating series test is a really good idea for these alternating series. Otherwise, I would use the test for divergence. Alrighty. Let's try a very simple looking one here. 1 over 2n plus 1. Alright, now let's see here. Now it may be tempting to be to say something like, oh, well, this is obviously going to be like the harmonic series, so this is going to diverge, so by the p-test. But remember, this isn't exactly a p-series, so we can't quite say that. So what we're going to do is we're going to use the limit comparison test, and we're going to compare this to 1 over n. Because this does look an awful lot like the harmonic series. So this will be our bn, and this is greater than or equal to 0, so we can use our limit comparison test. By the way, I just kind of default to using limit comparison test because then I don't need to really think about if my inequalities will go the right way with these signs right here. Anyways, if I do the limit comparison test, divide by the reciprocal, I end up with this limit here, n over 2n plus 1, and that ends up being 1/2, because again, limit of rational functions. Now 1/2 is in between 0 and infinity, so since this diverges by the p-test, then our original series will diverge by the limit comparison test. And remember, if we get something in between 0 and infinity, both our comparison and our original series do the same thing. Alrighty, so that one wasn't too bad here. Let's go to this one. N equals 2 to infinity of 1 over n square root of ln of n. All right, now this one is actually one of the generalized p-series, because this is 1 over n to the first, technically, and then we have ln of n to the 1/2. Now remember, with the generalized p-test, if our power of n is equal to 1, we look at the power of natural log of n. But the power here is going to be less than or equal to 1, so this diverges by the generalized p-test. So if you ever get a product of just n to the power and then log to a power, that's definitely going to be a generalized p-test, or maybe even just a p-test. All right. Let's see what do we have next here. All right, next it looks like we have the sum from 1 to infinity of 2 to the n. We'll stick with n's here. 2 to the n factorial over n plus 2 factorial here. All right, now whenever we see factorials, that's definitely a sign to use the ratio test. So let's go ahead and use that here. All right, so with the ratio test, we look at the limit as n goes to infinity of absolute value of an. Now I'm not going to write the absolute values here because everything is positive. So we have an plus 1, and then we have the reciprocal of regular an. All right, now let's see how this is going to work. So 2 to the n plus 1, well, we have one more 2 multiplied up here than we do down here. So that will just leave a 2. And then we have n plus 1 factorial divided by n factorial right here. Well, so if we were to look at this, this would be n plus 1 times n minus 1 and minus 2. This would be all the same thing, except we wouldn't have the n plus 1. So all of that cancels, and we're left with a single n plus 1. And then a similar phenomenon happens here, because this is n plus 3 times n plus 2, n plus 1. And this has all the same stuff except for n plus 3. So we end up with the limit as n goes to infinity of 2 times n plus 1 over n plus 3. Now this is going to equal 2 here, but last I checked 2 is going to be greater than 1. So this is going to diverge by the ratio test. Remember, if we get anything bigger than 1, it's going to end up diverging. All right, let's move on here. Next one that we have, n equals 1 to infinity, we're going to have n squared e to the negative n right here. All right, so what I'm going to do here is I'm going to rewrite this as the sum from 1 to infinity of n squared over e to the n. Now, this has got me thinking here, okay, this will probably end up converging because my exponential function is going to end up dominating my n squared here. But if I were to just compare this with 1 over e to the n, I would end up getting a limit that would go to infinity. And remember, we can't show convergence with an infinite limit, with limit comparison. So instead, what I'm going to do is I'm going to compare this with 2 to the n. So remember, this was a little bit confusing, but if you think that your default choice of bn might not work and 1 over e to the n won't work, then pick something a little bit closer to diverging that still converges. So 1 over 2 to the n is a bit closer to the threshold of like 1 over 1 to the n, which would diverge, but it's still going to converge. So this will be my bn. And then when I do a limit comparison test here, what am I going to get? I have n squared e to the n times 2 to the n right here. All right, now if I take this here and manipulate it a bit, this is going to be n squared over e to the n divided by 2 to the n. Now, e over 2 is a number that's greater than 1. So this is an exponential function with the base greater than 1, and here we have a polynomial. So this limit's going to end up equaling 0 right here. So since we got 0 from our limit comparison test and we wanted to show convergence, then the original series converges as well. So it converges by limit comparison test. All right, so let's refresh our page here. Let's see. All right, the next one here, we have the sum from n equals 1 to infinity of n squared e to the negative n cubed here. Okay, now this one's practically begging for us to use the integral test here because you can see that if you make your u be n cubed, then your du will look a lot like that. So let's get some practice using the integral test here. Although you could also do this with limit comparison, similar to the last one. So let's see here. So we need to make sure we're continuous. Well, this is a continuous function, so that's okay. Are we decreasing? Well, technically this e to the n cubed, I could write that on the denominator by getting rid of my negative here, and e to the n cubed grows way faster than n squared, so that's true. And then, are we positive? Well, exponential functions are positive, squares are positive, so we're all good. That means instead I'm going to do the integral from 1 to infinity of x squared e to the negative x cubed. All right, so as promised, I'm going to do my u substitution here. And I get that du over 3 will be x squared dx. So I have 1/3 the integral from 1 to infinity of e to the negative u du. And notice that my bounds will actually be the same here, because if I plug 1 in here, 1 cubed is 1. And if I have something going to infinity and I cube it, that will also still be going to infinity. All right, this integral ends up giving us negative 1/3 e to the negative u from 1 to infinity. And if I plug in the bounds, in e to the negative infinity will be 0, and then I'm subtracting a negative, so I have 1/3 e to the negative 1. All right, now remember, it doesn't matter specifically what number we get from our integral test. We just know that this integral converges, so the series converges by the integral test. Oops, sorry, I fell off the page a bit there. There we go. All right, but notice how this took a little bit more work than the other ones. So I like to use the integral test as a sort of last resort here. All right, moving on. Let's see here. Let's try this one. We have the sum from 2 to infinity of -1 to the n plus 1 divided by n ln of n. All right, looks like we have another alternating series, and remember, it's still alternating even if it's -1 to the n plus 1. That's an acceptable alternator. Do the alternating series test. Well, let's see, is 1 over n ln of n decreasing? Well, yeah, that's true. The top is staying constant, the bottom's getting bigger. And we see that if we look at the limit as n goes to infinity of this, we get 0. So this is going to converge by the AST. Very easy test. You can kind of just compare this to the integral test, how little work this ended up taking. Using the alternating series test is really nice if you have the opportunity to do it. All right, let's take a look at another one. We have the sum from 1 to infinity of sine of n. Okay, now this one's an open and shut case of a test for divergence, because if we look at the limit as n goes to infinity here of sine of n, so the sequence we're adding up, this does not exist, meaning that we don't get 0 from this, so this is going to diverge by the test for divergence. So if you ever suspect that whatever you're adding up won't go to 0, give the test for divergence a shot and see what happens. So this one's definitely going to diverge here. Okay, next we have the sum from n equals 1 to infinity of 3 to the n squared over n factorial. And right when I see that factorial, I know, okay, I'm going to use the ratio test here. Let's do so. I have 3 to the n plus 1, n plus 1 squared over n plus 1 factorial, and then I multiply by the reciprocal here. So I have n factorial, 3 to the n over n squared. All right, and then technically there should be absolute values here, but once again, everything is positive. But don't forget about these because we're going to be using these in the future here. Okay, now let's see. 3 to the n and 3n plus 1. Those cancel. The n factorial and the n plus 1 factorial, those cancel out. But then notice that I have an n plus 1 here and an n plus 1 squared there. So actually, those will cancel out too. So what will we end up getting here? We have the limit as n goes to infinity of 3 times n plus 1, but then there was nothing to cancel that n squared with. So we end up with 0 for this limit because we have a polynomial with a degree higher on the bottom, and that's less than 1. So this converges by the ratio test. So this goes to show you that even multiplying an exponential times a polynomial still can't end up beating this factorial, at least as far as series convergence goes. Okay, next, let's try this one. N squared plus 1 over n cubed plus 1. Now, this is another instance where you're like, okay, this is going to act like n squared over n cubed, which is 1 over n, so this is going to diverge. And that's the right hunch, but we need to use the limit comparison test to see that's going to happen. So I will compare this with n squared over n cubed, which is the same thing as 1 over n. This will be my Bn. Now, the series for this diverges by p-test, so we think that this might diverge as well. So if we look at our limit comparison test, which we are allowed to use because this is greater than or equal to 0, we have the limit as n goes to infinity of n squared plus 1 over n cubed plus 1, and then we divide by 1 over n. So dividing by 1 over n is the same as putting an n up here. Okay, now if we multiply through by this n, we have n cubed plus n over n cubed plus 1. And since we have polynomials of the same degree and same leading coefficients on the top and bottom, we end up getting 1 right here. And since 1 is between 0 and infinity, this series will do the same thing that the comparison did. So this is going to diverge by the limit comparison. All right. Let's see here. This seems like an interesting one. We have the sum from 1 to infinity of negative 1 to the n, 2 to the 1 over n. Okay, now originally this kind of says, all right, maybe we should use an alternating series here, or the alternating series test, but I'm not even sure if this goes to 0. So let's check that out first. So we have the limit as n goes to infinity of 2 to the 1 over n. Well, if I send n to infinity, this will be like 2 to the 0, which is 1. So this part isn't even going to 0, meaning that if we look at the whole thing, if we look at the limit as n goes to infinity of negative 1 to the n, 2 to the 1 over n, well, we know this part goes to 1, so this limit's not going to exist. And remember, if we don't get 0 specifically from this, we can say that this diverges by the test for divergence. All right. Next, I have another alternating series. We have the sum from 1 to infinity of negative 1 to the n minus 1 over the square root of n minus 1. Oh, this should start at 2. Whoops. Okay, so this is an alternating series. Negative 1 to the n minus 1 is also an acceptable alternator, though this time I think 1 over root n minus 1 will be decreasing because root n keeps getting bigger, and it goes to 0. Well, this is going to keep getting larger and larger and larger, so yeah, this is going to go to 0. So this series is going to converge by the alternating series test. So once you see that a series is alternating, you pretty much have one of these two scenarios here. It's usually either going to diverge by the test for divergence if this doesn't go to 0, but if this does go to 0 and it's decreasing, then we could say it converges by the EST. So usually alternating series fall into one of these two categories right here. Okay, time for more paper. Let's see here. Now we have the sum from 1 to infinity of negative 1 to the n, ln of n over the square root of n. All right, it's another alternating series, so let's practice what I just said. This is likely going to diverge by the test for divergence or converge by the alternating series test. Now let's see here. ln of n over root n. This actually is decreasing because root n grows faster than natural log of n does. And if we look at the limit as n goes to infinity, ln of n over root n is going to equal 0. Because of the hierarchy of functions, n to the 1/2 power goes to infinity more quickly than natural log of n does. So this is going to equal 0. So we get another series that converges by the alternating series test. And this demonstrates just how easy it is to use that test. So if you do see an alternating series, it's very likely a good idea to just go ahead and use the alternating series test there. All right, let's take a look at this one here. We have n plus 5 over 5 to the n. All right, now with this one right here, this is going to act a whole lot like 1 over 5 to the n, or n over 5 to the n. Now, since this is an exponential function, this is a polynomial, we have a suspicion that this will probably converge. But the thing is if we use something like 1 over 5 to the n, then that's just going to go to infinity because we'll have this n left over. So I'm going to compare this instead with 1 over 4 to the n. Now remember, whenever I want to compare something but I think my original comparison won't work, I make it a little bit closer to the threshold. So this is a little bit closer to the threshold for diverging, but this is still going to converge by the geometric series test. So this is going to be my Bn, Everything's greater than or equal to 0 here. So let's take a look at the limit. So we have n plus 5 over 5 to the n times 4 to the n over 1. Now, just like the earlier problem I did, I can rewrite this as n plus 5 over 5/4 to the n. Now, this base is bigger than 1, and it's an exponential function, so this will go to infinity more quickly than that does. We end up getting 0 here. And remember, 0, while it's on one of the boundaries for the limit comparison test, it's okay for showing convergence. So the series converges by the limit comparison. Okay, I think we're about halfway done here with the series that I want to go through. Let's keep going here. Keep powering through. We have n is 1 to infinity of negative 2 to the 2n over n to the n. All right, now here I see a bunch of nth powers, so like I did for the very first problem today, I'm going to try to use the root test here. Okay, so what's that limit? The limit as n goes to infinity of the absolute value of this stuff here raised to the 1 over n power. All right, now if I apply my 1 over n power here, let's see, negative 2 to the 2n is the same as 4 to the n, right? But then when I apply 1 over n to that, I just get 4. Meanwhile, on the bottom, if I apply 1 over nth power to this, I'm just going to get n. This ends up being 0, which is less than 1. So this converges by the root test. So again, when you see all those nth powers, the root test is definitely the way to go. Okay. Next, got an interesting looking one here. This is the square root of n squared minus 1 divided by n cubed plus 2n squared plus 5. Okay, so with this one, I'm going to look at the leading terms. So I have an n squared, but it's under a square root. So that's going to act a whole lot like n. And then on the bottom, my leading term here is n cubed. So I suspect that this is going to act a lot like 1 over n squared. And this is going to be my bn here. All right, and we know that as a series, 1 over n squared converges by the p-test. Let's do a good old limit comparison here. I think this one we could have done direct comparison as well. Actually, let's do direct comparison just for a change of scene here. We've done limit comparison a lot. So my an is the square root of n squared minus 1 over n cubed plus 2n squared plus 5. Now remember, if I want to show something converges, I need to show that it's smaller than something else that converges. So every step I want to make this bigger, so I can keep getting bigger until I get up to here. All right, so if I subtract something from the bottom, I'm going to get bigger. So I'm going to subtract 2n squared plus 5 from the bottom. Then if I add something to the top, that will also make things bigger. And then this will turn into 1 over n squared, which is my bn. So since an is less than or equal to bn, we have a positive series, and the series for bn converges, then the series for an, which this was an, this converges by, this time, the direct comparison test. There's an opportunity. We saw all the signs kind of line up here, so it was pretty easy to use the direct comparison test. Although limit comparison test would have worked perfectly well for this one. Next, we have something that we definitely need to use the limit comparison test for. We have the sum from 1 to infinity of tangent of 1 over n. Now remember, when we did the limit comparison test in class, I said that if we have tangent of 1 over n to a power, we can think of that as just acting like 1 over n to a power, or like whatever power of n was in here. So if this were 1 over n cubed, this would act a lot like 1 over n cubed, at least as far as series are concerned. Whatever this series does is going to be the same thing as this series. But since this diverges by the p-test, we know that this is going to diverge as well. Now, what test would we say we'd use here? Technically, this result right here is using the limit comparison test. So whenever we use this tangent or sine of 1 over n, we're really using the limit comparison test. All right, so this is going to diverge by the limit comparison test because it's going to act like 1 over n. Let's try another one of these. Say we have n equals 1 to infinity of n times sine of 1 over n. All right, now just like before, with sine or tangent, not cosine, but sine or tangent of 1 over n to a power, it's going to act just like the thing that's inside. So this is going to act a lot like n times 1 over n, which is 1. Okay, so we can take a look at this. The sum from 1 to infinity of 1 diverges by the test for divergence. So that means that if we limit compare these, this is going to diverge by the limit comparison test. Although based on the fact that we can compare this with 1, we also could have used the test for divergence directly on this. I think you would get 1 if you do that. So you could also use the test for divergence on this one if you recognize that in advance. All right, another one bites the dust here. Let's move on. All right. Getting these from a textbook, and these seem to get a bit more difficult as it goes on. So we might be seeing some harder ones here. All right, I have n factorial over e to the n squared. Now, right when I saw this, I know which test to use. It's going to be the ratio test. All right, so let's look at the limit as n goes to infinity. We're going to have n plus 1 factorial over e to the n plus 1 squared. Then up here, we're going to have e to the n squared, and then we have n factorial. And of course, we should have absolute value signs, but just like in all the other problems, this isn't going to matter too much here. Now, we've seen a million times how these cancel out. We're just going to be left with an n plus 1 here. Now, the interesting thing that's going to happen is how these exponentials cancel. Now, if I were to FOIL this out in the exponent, n plus 1 here, e to the n squared here, if I FOIL this out, this is e to the n squared plus 2n plus 1. Now, what I could do is I could cancel this e to the n squared with that n squared here, but I still have e to the 2n plus 1 left over down here. So what's going to happen is that this exponential function will go to infinity faster than this polynomial, so we're going to end up with 0, which is less than 1. So this converges by the ratio test. So factorials are powerful, but they're not going to be as powerful as an exponential function where the exponent is itself a quadratic. That's going to end up beating out factorials. All right, time to get to another page here. Let's see, we got about, 1, 2, 3, 4, 5, 6, 7 more here. And I think we'll be all practiced up. So we have the sum from n equals 1 to infinity of n squared plus 1 over 5 to the n. All right, I think we saw a very similar one to this earlier. I think it was just n plus 5 on the top. But just like before, it doesn't matter what kind of polynomial we have up here. We could have had n to the 100, for example, but it's not going to change what I'm going to use for bn. I'm going to use 1 over 4 to the n. Because if I use 1 over 5 to the n and I use limit comparison, I would be left over with that n squared plus 1, and that would go off to infinity, which I don't want because I think this is going to converge. So we know that 1 over 4 to the n converges by geometric series test. So let's take a look at the limit. We have n squared plus 1 over 5 to the n times 1 over 4 to the n. And then just like all the other problems where we've done this, I'm going to move this and combine it with that 5 to the n, giving us 5/4 to the n. Now 5/4 is bigger than 1, so this is an exponential function on the bottom, polynomial on the top. even though it's a square this time, it's still going to lose out. Since we got 0 and we're trying to show convergence, then we know that this series converges by the limit comparison test. Now, if we were trying to show divergence and we got 0, that wouldn't work out. But if we got infinity, we were trying to show divergence, that would be okay. But usually the ideal way to use limit comparison is get in between 0 and infinity. But you can use the edge cases for specific scenarios like this. Okay. Next, what's next? We have n equals 1 to infinity of ln of n divided by, n ln of n divided by n plus 1 cubed. Okay, this is kind of interesting here. What I'm going to do is I'm going to limit compare this with n ln of n n cubed. Because if I rewrite this, this is going to be 1 over n squared ln of n to the negative 1. And this is going to converge by the generalized p-test. Okay, so since this is a series, will converge by the generalized p-test, I suspect that this will converge as well. Let's do a limit comparison to see if that works out. We have the limit as n goes to infinity of our original. And then we take the reciprocal of our new one here. So that will give us n squared ln of n to the negative 1. Now if we see how all of this will cancel out here, let's see what's going to happen with this. Well, we have these natural logs canceling, and then we just have n cubed over n plus 1 cubed. But that limit is just going to end up equaling 1. Since we got 1, and this converged by the generalized p-test, then this will converge by the limit comparison test. I'm not sure if I mentioned this in class or not. If I didn't, I probably should have. The limit comparison test is more or less the glue that kind of holds all of these series tests together. Kind of like the chain rule with derivatives and U substitution with integrals, the limit comparison test gives us a lot of flexibility when it comes to these series tests. Okay, let's keep going. We have the sum from 1 to infinity of e to the 1 over n squared. This is another one that's pretty much asking us to use the integral test, because if we did u as 1 over n, du would be negative 1 over n squared, getting rid of this. But a better way of doing this would be to do a direct comparison with 1 over n squared. Actually, sorry, not a direct comparison. We want to do a limit comparison. Why is that? Well, if we look at the limit as n goes to infinity, we have e to the 1 over n squared times the reciprocal of this. So those will cancel out. And then we have the limit as n goes to infinity of e to the 1 over n. That will just be 1, because my exponent is heading to 0, and e to the 0 will be 1. So this means it's going to converge by the limit comparison test. Okay, now how did I know to select this as my bn here? Well, e to the 1 over n, the bigger n gets, the smaller the exponent will get. So this is going to end up converging to 1. That's what made me think of just putting a 1 on top to replace it. Kind of like how arctan of n heads to pi over 2, and putting a pi over 2 in place of that wouldn't be bad. You could do the same thing with this and replace it with a 1 here, if you sense that some kind of function is heading towards a specific number in your series. Okay, just a few left here. Let's take a look at this one. We have j is 1 to infinity, negative 1 to the j. Okay, so this might be alternating. And then we have root j over j plus 5 here. Okay. By the way, so I'm not going to use n 100% of the time with these indices. Some other common indices you might see are m, j, I. Occasionally, or yeah, you see k's pretty often. Sometimes an l, maybe if you're running on the letters.
But yeah, get used to seeing other things other than n here, because occasionally we'll see that. So this is alternating, because we have -1 to the j. Now, if we have this here, we need to see if this is going to 0 or not. If it's not going to 0, we could use test for divergence. But if it is going to 0 and it's decreasing, then we could use AST. And I suspect this is going to go to 0 because we have a square root over just a linear term. So is this decreasing? Well, yes, it is, because we have a square root and then a linear term on the bottom, and linear terms go to infinity faster than square roots. And for that same reason, we look at the limit as j goes to infinity of this, we end up getting 0. So that's our other criterion for the alternating series test. This is going to converge by the AST. Okay, next we have kind of an odd looking one here. We have n is 1 to infinity of n factorial to the n over n to the 4n. Now, I can't emphasize enough how fast these functions are going. These are both going to infinity ridiculously fast. Like even if you plug in single-digit numbers in here, it may break your calculator. Like it goes to infinity that big. All right, so let's see here. I see a bunch of nth powers. So that kind of suggests to me that I should use the root test here. Although the ratio test would have also worked, but I think that would have been harder. Let's use the root test. We have the limit as n goes to infinity of n factorial to the n over n to the 4n all to 1 over n. And as usual, we can put absolute values here, but everything's positive. Now, if I apply 1 over n to each of these, I have the limit as n goes to infinity of n factorial. Now, 1 over n times this will give me n to the 4th. Now, in terms of the hierarchy of functions, this is way higher on the list than n to the 4th is. So this is going to go to positive infinity. So this is going to diverge by the root test. All right. That was a good root test one. Okay. All right, let's do our last one here. So this is the sum from 2 to infinity of 1 over natural log of n raised to the natural log of n power. All right, now I had to come back to this one because I accidentally made a mistake in the previous recording here, so I want to do this properly. So what I'm going to do here is I'm actually going to try to use the integral test. Now, if you try to do the root test, which might be kind of tempting because of this, unfortunately, you'll end up with 1. This does go to 0, so we can't use test for divergence. It's not alternating. And I don't know, I don't see an obvious thing to do a direct comparison with. Although, yeah, maybe I'm missing something, who knows. But anyways, what we need to do is we need to figure out what we're going to do for this series. And for this one, I'm going to use the integral test. This is positive, decreasing, and continuous, at least as far as 2. So let's go ahead and do the integral test here. So this is going to be a little bit different from usual, and I'll show you why. So we have ln of x to the ln of x. All right, now usually I don't use the integral test unless I absolutely have to, or it looks like something we can use the integral test on. Now here what I'm going to do is I'm going to do u as ln of x. Then du will be dx over x. Now I don't have an x in here, so I'm going to bring that up here. And in terms of u, if we exponentiate both sides here, e to the u is going to be x. So this is technically e to the u du is dx. So what does that say about our integral here? Well, let's see. This will now be the integral from ln of 2 to infinity of 1 over, or sorry, e to the u over u raised to the u power. Okay, now I don't know about you, but I don't really want to integrate this function right here. This is going to be too hard. But surprisingly, remember one key aspect of the integral test is that if the integral does the same thing that the series does, provided we're positive, decreasing, and continuous. And this is still satisfy those requirements. So this is going to do the same thing as the series, n equals, I guess we could do 1 to infinity of e to the u, or sorry, e to the n over n to the n. Now this is something that we can use the root test on. So we have the limit as n goes to infinity of e to the n over n to the n to the 1 over n. And if we apply that here, we have the limit as n goes to infinity of e over n, which is 0. 0 is less than 1, so this converges by the root test. Now this series converges by the root test. That means that this integral converges, which means that this integral converges, which means that this series converges. So we kind of had to work backwards here. So ultimately, we could say that this series converges by the integral test. Ultimately, that's what we used here. Now, if we tried to use the root test immediately, we would end up having to do this limit. Limit as n goes to infinity of 1 over ln of n to the ln of n over n. And this actually ends up being 1. So that's going to be inconclusive. And if we just analyze this directly, maybe with a direct comparison test with something, that's not going to work out too well either. So ultimately, the integral test is kind of our method of last resort, but as we can see, it can be pretty powerful to use the integral test in this way right here. So this is definitely a very challenging series here. This one was definitely a frowny face. All right, well, that's about it for now. So we've definitely gone over a bunch of different types of series, and hopefully through that practice, you guys have managed to build up your intuition about which tests we should use when. And as a homework assignment, I've also given you a few other series to look at, some of which are going to be relatively straightforward like the earlier ones, but there may be a few kind of more similar to this one where we have to think outside the box a little bit. All right, that's it for this lesson, so I will see you guys next time.